could ask you to find a question. I know, I cannot believe it, yeah.
All right, let's, once you get settled in. I wanted to start by saying that it's my utmost honor and privilege to introduce Matus, who doesn't need introductions, but here I am. He's from NYU, and one thing I have to say is, like, if you have ever met Matus in person, he's probably one of the most humble and self-effacing person I've ever met in life. Maybe to the point of being a little self-deprecating. So I'm sorry, Matus, I'm going to have to counteract that a little bit by speaking about all your glorious achievements. Matus is one of the OGs of deep learning theory. In fact, last night over some beers, Ankur claimed that Matus is like the Mike Jordan of deep learning theory, not Michael I. Jordan, but Matus. He's done tons of work in deep learning theory, ranging from things like implicit bias for optimization to generalization bounds for neural networks to the benefits of depth in neural networks. And I mean, just going beyond deep learning theory, he's also developed an absolutely heavenly theory of convex analysis and infinity with Miro Dudik and Rob Shapire. And if you thought that Matus was like was one-dimensional mathematically, that's not quite right, because in a previous life, or maybe even now current life, he was an accomplished violinist with a degree from Juilliard, which is probably one of the most prestigious music schools in the world. So I'm just glad that he chose to actually make music with pen and paper instead. So please join me in welcoming the glorious Matus Telgarsky.
Thank you very much for the invitation. I'm very happy to say this will be one of my more technical talks. In particular, I'm going to set the record straight on everything that Satyen just said. I would also like to draw attention to all the people who heavily influenced me and helped with the preparation for this talk. So let me just give a bit of an explanation for what I plan to talk about and why. Basically, we had this Simons program in the fall, and as I prepared for it and thought about all the open problems facing the community, the fact, we're just getting progressively more and more behind, as I started formulating open problems, then I had to think about why we're having trouble solving any of the open problems we have. Then I had to think about all of the sociological issues. It just kept snowballing. More and more things kept accumulating. Every time I met a top theory student in Berkeley, they tell me they're on the job market. I'd say, did I miss your application? They'd say, no, I'm only considering OpenAI. All these things were in my mind, and I realized that actually the technical problems are the least of our problems. So that's why I actually feel unethical making this a purely technical talk, because we have to discuss why the technical problems had their own problems. So the plan for today is as follows. So I will spend most of the time, I claim, on technical questions, which are somewhat mathematically stated. Then I will discuss speculative questions where all respect for me will go out the window because they sound pretty stupid, but I hope they can. My goal in both of these parts is to say something orthogonal from what you might hear elsewhere. I mean, we know that there are all sorts of things we don't know how to answer about convergence rates and diffusion models, and we have so many questions, and every single talk left a million open questions, things we don't know how to solve, oracles to simplify, assumptions to remove. I'm trying to say something a bit orthogonal from what you've heard. And then last, I'll say the sociological part. So in terms of the scope, I mean, there's so many topics I will not cover. I'm kind of sticking to my expertise, but I will veer very quickly from my expertise, in which case, if you think I say something stupid, I definitely said something stupid. I request that you tell me rather than somebody in the hall right afterwards. Let's just say it, just let it out. So that was actually not the first stupid thing I said, but thanks. There are many topics that are full of own problems that I'm not covering due to expertise. I'm also saying that for those of you that came here for pure entertainment thinking I'm going to repeat the 1 hour long rant I gave at NeurIPS where I basically got myself fired, I will not do that, though I have purified, I think, some of the content of the firing discussion into the sociological questions at the end. Okay, so that is the plan for today. Okay, so let's get right into it. The first open problem was set up for me by Francis. So for the technical questions, there'll be 2 problems, and they will have 3 parts. And so I know this is vague. Just give me some time to make it slightly more precise. So when deep learning happened, the claim was it happened because it does automated feature learning. We never proved this. And there are cases where it's false. It's not generally true. So we didn't prove this. So I'll give you more detail, but there are 2 reasons why I like this. Not just because it's an empirical promise. It's clear that there's beautiful mathematics we've overlooked. There are beautiful mathematical reasons hiding in all of the things we did not prove. It's not just like, applying a stronger, shaving some factor or something. There's beautiful mathematical phenomena we haven't even characterized yet. And that's one of the reasons I worked on deep learning theory. That it needed new textbooks, not old ones. Okay, so to make a more precise version of this, let me tell you about what for many of us in the field is sort of one of our favorite questions, which is something called the 2XOR problem. I'm giving a citation to Colin Way and a lot of other people. I'm giving this citation, though of course we all know that things like Boolean formulas, polynomial learning, it goes back to like day 1 of machine learning in a century ago. But I'm going to use this because it's familiar to a lot of us and it has very interesting properties if you haven't seen it before. So here's the setup. So I'm using a 2-layer ReLU network. Okay, so how is this defined? I form an affine mapping of my input. I delete the negative part, and then I hit it by a scalar. I do this m times. Okay, very, very simple predictor. The data is just uniform in the corners of the hypercube normalized CL2 norm. The labels are just +1, -1 on the first 2 coordinates. Okay, I just normalized, that's why the D is there. I'm using the logistic loss. And what I'm going to show you here are the trajectory of the particles. So what I'm doing is I'm taking the inner layer and I'm multiplying by the outer layer. So there's m of these. Okay, I'm going to show you these over time. And Francis already showed you a version of this, but I'm going to show you many of these. And in the left plot is what happens if you train both layers. And in the right plot is what happens if you only train the outer layer. And this is at Gaussian initialization, which is semi-standard. And what I'm showing here are the first 2 coordinates. So the first 2 coordinates where all the action happens in this problem. That's where the labels are determined. Okay, so again, left plot, first 2 coordinates, right plot, unregularized gradient descent, just standard gradient descent, full batch gradient descent. Okay, if you've seen this before, I don't care because every time I run this plot, I am shocked by what happens, even though I have an infinite number of theorems about it. Okay, here's what happens. So the left plot, it extremely cleanly follows 4 directions. No explicit regularization. No tricks inside the initialization. I mean, it just extremely cleanly follows 4 different paths. And there's so much we can say about this. Actually, for gradient descent in the limit, there's only going to be 1 particle on each of those 4 directions. The other ones are going to lose asymptotically. And in the right plot, you see it cannot adjust the inner layer, so it has to follow these straight line paths. Okay? For me, every time I see this, and every time I rerun it, I'm just completely shocked. And by the way, just a side comment, if you notice the first slide I credit 03, I did not write this code. And that is a lesson for all of us theorists. We have no excuse not to run experiments now. because I just asked O3 to write it for me, and I just read the code and made sure it was not running Atom by accident. Okay. So let me show you another view of this, because you might say, oh, I'm obscuring part of the key story. There are actually two things we have to learn here. We have to do the right thing in the subspace of the first two directions, and we have to do the right thing orthogonal to it. We can't pay attention to the noise directions. That's why this is an interesting question. And here I'm plotting the noise directions. So the horizontal axis is the progress, the norm along the first two dimensions, and then the vertical axis is the norm along the remaining dimensions. Okay, so there are d minus 2 dimensions on the vertical axis, and there's 2 dimensions on the horizontal axis. So it's actually, we should expect an initialization, the norm to be larger in the vertical axis, which is indeed what we see here. It goes like this because there are d minus 2 coordinates, same initialization scale versus 2 coordinates. Now, just to make these plots a little bit more clear, I'm going to tell you what's going to happen in advance. We want the feature learning to ignore the d minus 2 extra dimensions. Okay? And that is, so the left two plots are what happens with gradient descent, and with both layers, and the right plot is, the right column is only training the first layer. Sorry, only training the second layer, so convex problem. And this is what you see. So when you train both layers, it just does not care at all about those other dimensions. It just only moves in this direction and even slams down and zeroes out things. And then in the right column, you see it is forced to preserve these terrible noisy directions. Okay? Okay, by the way, this is my favorite set of figures in all of machine learning. I've written the code myself probably like 50 times, and I've had O3 write the code like 20 times, and I spend like an hour a day watching this, like half of. So that was like one of the nice reasons to prepare this talk. I get to watch all of this again. No, if you guys think I'm crazy, like I mean that's fine, but I have appendix slides running different algorithms and all these different choices. It's different for Atom, all of these sorts of things. Okay, so what can we say about this? So to make the question more precise, this is version A of problem 1. So necessary and sufficient conditions on feature learning. So separate the sample, to make this a more precise question, separate the sample complexity of learning in some model class, for instance, the 2-layer training, versus learning. Now, if you haven't seen this before, let me explain it. This is sort of like training only the outer layer. This is a convex problem in WT, okay? This thing here is convex WT if L is a convex function, like use a convex loss. So this corresponds to learning in an RKHS. For those of you that know some lingo, people call this the NTK. It corresponds to sort of staying near initialization, which can happen as you increase the width. There's an infinite amount of beautiful papers on this topic. I will not talk about that. I'm just using that as a baseline. So here the challenge is to prove that we can do better than the initial RKHS. And again, the initial RKHS is the only general tool we have for the study of this kind of optimization process. In very general settings, it can tell us sort of what happens if we stay near initialization. And so now let me tell you the positive results about feature learning. So if you look at the example I just showed you, the 2 XOR problem, and you put some conditions on it, you have some initialization conditions, and you run SGD with a batch size of D, then you can show a very strong sample complexity separation. The RKHS needs D² samples, whereas learning with the features, running SGD needs only order D. Okay, so this is why I'm calling this a feature learning theorem. It says that we need fewer features. That's sort of a smoking gun that you're actually doing the right thing and learning along those 4 directions. This is a proof by Margaret Glasgow, who might be here. She's probably hiding to not be embarrassed. Oh, okay. I will not imply where she is because I'm just embarrassing her, but this is actually my gold standard proof in this area. This is my favorite paper, so I highly recommend you read it and explain it to me. So, okay, about the status of this question. So the NTK I'm treating as a baseline, and again, why am I calling this a forgotten problem? This is the reason I have to make a talk like this. We're dealing with things like LLMs where we don't even have a 1-layer ReLU network. We've moved on from ReLU to SILU to SWIGLU. Then we replace that with mixture of experts. It's 3 layers, okay? And then we embed this with, and then attention and normalization layers, right? All of this stuff, multi-layer version of this. We don't even understand this basic thing. We did not understand this basic thing. Modern papers that tried to understand gradient descent on a transformer, they delete the MLP, or they freeze it. So I'm just reminding everybody, we never solved this problem. And that's a sociological question. Why didn't we solve this problem, and how are we going to get around this in the future? So that's, again, why I have to make this talk. Okay, let me get back to the technical part. So I've told you the baseline, which is the NTK. My favorite result of this flavor is this, but that proof already breaks if you go to 3 XOR. It has fundamentally different structure, the parity of 3, and the parity of 2. Completely different. And the proof breaks. Then, and it's a 50-page proof with like infinity IQ on every page. So that's what it takes to do these problems. And we have some tools that seem to work in general, like the mean field, but they actually have to modify the gradient descent process in a non-trivial way. It's not practical gradient descent. And Nati and myself and a bunch of other people worked in this margin theory, but it also has an infinite number of assumptions. So just to summarize, I just wanted to remind everybody, it's not what Francis said about 2-layer training or 3-layer training being problematic. We don't understand 2-layer training. We don't even know what it's doing in practice. So I'm just reminding everybody that this is a completely wide open, major open problem still. Take Marguerite's proof, make it 3 XOR. Take AlexNet, VGGNet, transform any of these, and prove in a generic setting that feature learning is happening. Any questions? Yeah.
I guess I'm not that familiar with deep learning theory, but there are a few different definitions of feature learning that I've seen, I guess. So I'm just wondering, like, specifically, what is it defined for you here?
Yeah, and I should be totally honest. I sent these slides to a friend last night who's an expert, and he actually told me to remove the feature learning terminology from all the slides, that it's too vague, and he's just frustrated that I use the term at all. So I chose, so maybe it's a little bit of like a popularization, so there is some vagueness. My personal preference is to use sample complexity as the gold standard to measure feature learning. So you define some class as being no feature learning, in this case, the NTK, and then you have another class, and you want to beat a lower bound for the no feature learning class. So in this case, we call the NTK no feature learning, because it's just an RKHS, it's a convex method. We have sample complexity lower bounds for that, and our goal is to beat that lower bound.
Okay, yeah, that makes sense, thanks.
I can make one more comment, which is this implies many of the other intuitive definitions of feature learning. So for instance, the fact that you follow these 4 directions, this is the mechanism of Marguerite's proof. So other intuitive notions of feature learning are consequences of this one. And that's why I treat this as a gold standard, but that is just my opinion. Okay, any other questions? Yeah, Vitaly?
So maybe just to clarify, the open problem is that you have some, let's say, distribution, a specific problem, where you know the neural network always solves it, it's like completely reliable, but you don't know how to prove it, like for some specific examples. Is that the kind of the target question and that you need to understand?
I'll give you like 70 open problems real fast.
No, but so, a clean, simple one.
Okay, but I'll just give you a few. So one is take Marguerite's proof. First of all, make the initialization standard.
Okay.
Give me 10 years, I can't do it. So make the initialization standard. That requires new mathematics. 2, make it for more than 2 XOR, make it 3 XOR. Okay? 3, make it for more layers. Okay? 4, start considering standard architectures that include convolution layers normalization. 5, include the transformer.
I would like to first understand what is the actual problem that you're solving as a mapping from data to labels. Like
yes, the goal is
it
test error.
Just a XOR on a Gaussian distribution or Boolean hypercube or?
You can use those simplifications if you wish.
Okay, so you're saying, okay, let's say 3 XOR is solved by some.
This problem is so hard that you're welcome to make basically any assumptions you want. Okay, so let me tell you a strategy to think about and work on this problem. So if you noticed when I was showing the particles, they followed a very clear path. And this is not something restricted to non-convex problems. So what I'm going to show you here, so I'm going to show you again the 2 XOR. Now with Adam, I leave it as a fun exercise for you to see what's different with Adam versus what GD did. But here I'm just going to run linear regression, okay? shouldn't have actually spoiled the surprise. But I'm going to run linear regression. And I want to point out that for linear regression, we have an extremely clean characterization of the path followed by linear regression. Again, what I'm showing you now is a strategy to solve that problem, inspired by what gradient descent did, where it followed a very clean path. I'm saying, oh, let's just prove lemmas that gradient descent follows certain clean paths. Here's something you can say for least squares. So if you write out the covariance of the data matrix and you look at its SVD, and you look at the progress of gradient descent along these SVD directions, the right linear vector directions, if you just write out the progress towards any optimum along those directions and just unroll the definition of gradient descent, you get this equality. And what does this equality say? It says that you're contracting at an exponential rate along every singular vector, and that exponential rate scales with the singular values. What does this tell you? It tells you that if the covariance is highly ellipsoidal, gradient descent is not following anything like a straight line. It's following a rectilinear curve. It has right angles in it. Everybody follow that? So if you run gradient descent, indeed, it has a near right angle in it. This is gradient descent on on least squares. It's a right angle. So there's an unlimited number of these path-following problems which are open in the convex case. In the general convex case, I can say essentially nothing about the path followed by gradient descent. And it's going to be on the next slide, but I'm proposing this as a general strategy to solve the previous problem. So for the 2 XOR case, Margolit's proof and intuition is all about following these 4 directions. And I'm proposing looking at gradient descent and studying the paths followed by it and using that as a lemma, and also a beautiful phenomenon in its own right, but using it as a lemma to solve these feature learning problems. Okay, so here's the claim, or the question. So nesting sufficient conditional feature learning, characterize the path followed by GD. For example, for logistic and linear, I showed you least squares and linear. For logistic and linear, find D orthogonal in some geometry vectors that are followed. Okay, so for a ellipsoidal covariance data matrix, least squares follows a rectilinear curve with right angles in it. Do we have anything like this for logistic regression? I don't know. Nobody knows. Okay. Let me tell you a little bit about this problem. So there are a few scattered results. So Margolit's proof, when you read the details, it is doing very careful tracking of where everything is moving. So for me, it's an instance of this. Jingfeng Wu, who's this super genius at Berkeley, he has a proof about logistic regression in high dimensions, and it shows that logistic regression also follows a right angle. If you follow the end of the right angle, the asymptotic direction, the maximum margin direction, you get a terrible test error. You have to stop early before you pass the right angle in order to get a good test error. So this is the point here. It's not just a visualization trick. What I'm trying to say here is that in practice, we stop early, and the early stop direction is often uncorrelated with the asymptotic direction the textbooks tell you about. So even in the convex case, gradient descent is doing something much different from our asymptotic understanding and our regular convergence rates and stuff like that. So the point, the real meaning of this question is to analyze early stopping and its statistical consequences. And we do have some of these statistical consequences in special cases. But in general, I do not understand the path followed by gradient descent. And my dream is that if we can solve this for the convex case, then it gives us some help and some ideas to handle the non-convex cases. And I should say that this is out of my depth, but the more I think about this, I see this everywhere. When I hear people talking about things like post-training versus pre-training in LLMs, I'm thinking, okay, so the gradient descent path went like this curve, and it stopped somewhere in this curve, and then you ran your post-training from there, and obviously it's going to do completely different things based on if you were beyond a right angle or not in the initial pre-training phase. So I would like to hallucinate that this has many consequences, but already in the convex case, this is a difficult problem. Okay. And Vitaly was kind of requesting that I'm a bit more precise when I state my questions. So one version of this is, if you could find some reasonable setting and some analog of the SVD and characterize the directions followed by logistic regression. There are easy cases you can handle with like an extreme covariance matrix, but yeah, that's one version of this question. So any questions about this? Yeah.
So maybe just to understand, the difference between the open problem here and the previous slide is just the change of the loss?
No, you can use whatever loss you want in the other one. For this one, you can just use any convex loss. What I was saying okay, so to be clear, for this specific EG, yes, it is to just swap in the loss. The more difficult part is where I put orthogonal in quotes. So if you run logistic regression on this same exact data, I don't have it here, but I've run it an infinite number of times and stared at it in the middle of the night. Here's what logistic loss does. It follows least squares up to the right angle, almost bit for bit, and then it goes like this. Okay, so this is no longer a right angle, but it might have to do with the funky geometry implicitly followed by logistic regression. So the more difficult part of this will be, first of all, translating the orthogonal part. Also, as everybody knows, I mean, least squares is just a mathematical construct. The goal of least squares is to make the math easy. So you're not going to get equalities anymore.
So I have a question about the earlier question. So do you know any settings where if you train on 3 XOR problem, you get feature learning? Do you know any reasonable setup that you would consider like reasonable by your notion where feature learning happens?
Wait, I mean, that's what Marguerite's proof establishes.
3 XOR.
Oh, 3 XOR. Yeah, well, we do have scattered results, but none of them in the strength of Marguerite's proof that really go, honestly, from standard initialization. I mean, you can also look at these staircase papers and things like that if you like those where you can analyze the leap complexity of the x1, x2, x3. So, I mean, those papers do imply that you learn that thing, but it is a modified gradient descent method. But for a pure gradient descent method from a reasonable initialization, there is no such proof.
Okay, so you are talking about d square versus d cube gap. So no feature learning is d cube, and like what is the sample complexity of feature learning that you are targeting?
Okay, that I'm not going to get too much into because then that gets into, I don't know of, so for learning in the RKHS, I think probably, yeah, this one, my recollection is that under some initializations we can prove a d cubed versus d poly k. This is the kind of thing we can prove.
Oh, d poly k, okay, that's...
Yeah.
Okay,
Yeah.
thanks.
Can I try to understand maybe this slide and the next one better?
Mm-hmm.
So it's like, is it something like it's hard to generalize some like clean feature learning results for 2XOR to like other settings, like maybe other models or other problems? Is that like, and maybe you're proposing that like characterizing the GD path is like a more general framework that might be able to, I don't know, like do this? And is it like this path thing, at least for 2XOR, also characterizes like some feature learning stuff?
Yes, that is
Okay.
exactly my goal here.
Okay, okay, I see.
And I should also say that it was beautiful and interesting to me that already in the convex case, this problem is extremely difficult and has very strong consequences. Like I said, this paper by Jingfeng, it analyzes a high-dimensional setting where the asymptotic max margin solution has terrible test error according to 0,1 and according to logistic loss. So it points in the wrong direction, okay? And you have to stop early, and you have to use a different proof technique.
Okay, thanks. And maybe just for the previous slide, like, could you maybe repeat what this like right angle thing is and like how it relates to the?
Yeah, so what I'm trying to point out is that if you open a textbook, people often say that convex optimization is closed. I had to deal with people saying this all day when I was a grad student. And you open up a standard textbook, it talks about an optimum. For some reason, people think they exist. And, but it says there's an optimum, and it says you converge it to some rate. What I'm pointing out here is, for this statistical problem, you might not want to converge to the optimum. So what happens, first of all, gradient descent follows this path, but I'm also trying to highlight this path has meaning. In a lot of statistical problems, this direction is pure noise. This direction constitutes overfitting to label noise. And this direction is actually the population error, the direction you want to go in. So I'm saying two things. First of all, I'm saying gradient descent follows this path, But I'm also saying it has very strong and very important meaning and very important consequences when we care about test error.
Okay, thanks.
Yeah, you can't get any hints about this from a classical view of optimization. Okay, so now I will, okay, let me make a few adjustments. I'm going to, so for those of you that have not been in one of my talks before, no matter what I say at the beginning of the talk, I always mismanage time. It's just my ritual. So what I'm going to do, because it's actually more important for me to hear you guys than to hear myself, I will still take lots of questions. Just don't feel stressed. If I miss half the slides, I will post them, okay? So again, don't feel stressed, and I'm also not going to take 10 hours. Okay, so I want to say that there was an experiment I failed to produce for today, even though I tried quite a bit the last few nights, which is I wanted to exhibit a clean path followed by the attention matrices, and I failed. If you watch the evolution of the attention over time, it actually does not follow a clean curve. The next thing I'm going to try is plotting the Q and the K matrices, but then I have to embed them in a low-dimensional space and pick the right low-dimensional space. I believe this problem can be solved. I failed to solve it for today, but I just want you to know that I definitely was not restricting myself to even MLPs in any of what I've been thinking about. I am definitely targeting transformers here. And I completely believe there's going to be a clean path. I just didn't find it yet. Okay. Now, a lot of you might say, wait, Matus, you're saying there are sociological problems. You're telling us that we spent 10 years with all these big brain people not able to crack the basic questions we set out to solve. How are we going to make progress? It is not my goal to make everyone feel sad. We have to change what we're doing. And that's what I want to tell you about. So another thing, one way we can change what we're doing is I feel very bad that in the last 10 years for deep learning theory, we did not produce what I call a conditional optimization theory. So if you do a complexity analysis, complexity theoretic analysis of, like you're in TCS, you just say if P is not equal to NP, and you don't even waste any time thinking about it, right? You don't sit there for like 2 days like, wait, maybe P is equal to NP and like go, you know what I mean? But that's actually how we're approaching optimization. Every time somebody approaches an optimization problem, they like sit. And so what I'm proposing is that a group of us should just really commit to finding a very strong oracle model of what gradient descent is doing. I wrote one version of it. Poly 1 over epsilon finds F with loss less than epsilon, regularization less than 1 over epsilon, okay? The challenge, of course, here is figuring out what regularization is. So let me say a bit more about this. So again, the goal here is to make progress on this problem by splitting into 2 tasks. 1, characterizing what actually gradient descent is doing, just empirically finding what it's doing, and then 2, a mountain of big brain people can go prove it. And this, for me, is something we have not really done. And I'll explain why I mean we haven't really done, because you might say, wait, Matus, I know about this 1,000 papers that you didn't mention. So again, splitting the effort, and empirically, it's hard to find this inductive bias. So something you can see in the literature is, for instance, in RL and a lot of the talks here, there were oracles of various types, 0-1 loss oracles, squared loss oracles. All people use L2 regularization for the regularizer. None of these actually match what, especially with early stopping, gradient descent and Atom are doing on things like LMs, on things like, so we really are not using the right oracle model. Okay, I think we're all aware of this, but it's not, I've seen talks, people say, oh, we're using a 0-1 loss oracle and this is intractable. No, that's not even 1% of the problem. You switch that with the loss, it's still not related to what practice is doing. And it's not just that we want to follow practice, it's that practice is doing something beautiful that we don't know about. Okay, like these right angles that I surprised half of you with. So, or no, maybe just surprised myself with it. So, yes, so the task here is to identify empirically this regularization. And yeah, and I should say, there are papers, like the work by Nanti and colleagues and stuff I also did with the implicit bias, but that's under many, many conditions. And if you early stop, it's something very different. And let me just say that it's really not clear what this is. Like some of the max margin results, they relate to some class called the F1, which Francis termed and talked about, and we know in general this thing is NP Hartz. That's definitely not what's happening. So this question's wide open, empirically and mathematically. Okay? Any questions about this? Let me say it another way. So there was a nice paper, I think 2 days ago I was sick and I didn't come to the deep learning session, I apologize. And in that session there was a paper about these multi-reasoning problems. And they they were not able to train an MLP. They had to remove the MLP. Instead, we could have, if we had just provided them with an oracle, they could have just used it and just split concerns, right? This is a paper about attention and things like that, sure, and make an assumption about what the MLP is doing as you train. So that would be my goal, so that we could produce a nice MLP or MOE, a lemma that everyone else, or assumption that just everyone else could use, so that new papers don't have to like prove everything from nuts and bolts. Okay? Okay, there's a question?
Hello. So maybe this is a naive question, but all of the results we have about learning, let's say in like this feature learning setting, kind of depend very like sensitively on the assumptions on like statistical assumptions on the data, and like I guess how can we bridge the gap between, let's say you have all this optimization theory and you have all this statistical theory, and like how do you relate the statistical assumptions to the optimization landscape?
Yeah, so this is an excellent question, and this question literally keeps me up at night. Sometimes I think, okay, I just spent a week trying to prove something which is probably false in like any generality. The only answer I have to you here is to accept making a lot of assumptions for now, try to make them a little different from prior work, and run lots and lots of experiments. I do not have a good answer to this question.
Yeah, so another follow-up to this. So it seems like also there's a lot of things about natural data that kind of dictates, because you run different models, like depending on, like, if you change the architecture, maybe you don't see that much of a difference. So maybe there's something about natural data, like do you know?
Yes, I would like to say this is a sociological problem. I have heard people say, but it's a great question, it's actually the best question. People have been talking about something about natural data being the reason why deep learning actually won, right? I mean, look at how many of our proofs go to the polynomial learning, right? If you want to learn polynomials, you should just learn L1 regularized polynomial regression. It's log D, right? It's K log D. There's no D, there's no poly D, right? But the reality is that the world, for some reason, is not polynomial. This is the open problem, and I've heard people talk about it for 10 years. There's a few papers, but this is extremely difficult to crack. You could view that morally. The true version of this empirical problem is the natural data characterization. It's embedded in the regularizer. But there has been no concerted effort on this. And let me just make a pointer to like what I'm going to tell you in 10 minutes. This is the sociological problem. For some reason, the community has not worked on these questions. It's very weird. And it's, I mean, I'm part of the blame, right? Like I'd rather go like read a book on concentration inequalities than play with data, but okay. All right, good. You guys are getting me into like my trying to get fired mode, so it's good. Like we will enter that part of the talk pretty soon. So,
thank you.
Speaking of which, in order to get to that part of the talk, what I'm going to do is I'm going to toxically laundry list a few questions, a few problems, so that we can get to the other material. So I apologize. I'm going to laundry list. I'm going to try to make it semi-intelligent so that you can actually remember what I say afterwards, and just so that we get to everything. So problem 2 is approximation theoretic. I'm just going to state the questions, and then at the end of this 3-part, we will then take questions. So it goes like this. Problem number 1, theory of depth in MLPs, open. No, I did not close it. I actually prefer the 2 to 3 results by Eldon Shamir and Daniele. Hey, Amit, I saw you like a minute ago. For higher depths, there's my construction, which says that there's an exponential separation that you can get with a couple more layers. Not empirically relevant. My work has no relevance to why networks got deeper in practice. It's the huge embarrassment of my life. Okay? I'm dead serious right now. It feels awful. I feel like a clown about it. No, I'm totally serious. And even more disastrously, I constructed a set of basis functions which then launched all these other works. And the reality is we never solved this problem. So the question of empirically why practice went from AlexNet to VGGNet to ResNet is open. Approximation theoretically, what are those networks actually doing with depth? So open problem, not closed. 2, I'm very happy to say that I really like what the LLM community has been doing with depth. I actually feel that they're taking a very good approach, which is very inspiring and has lots of new ideas. And to my surprise, the LLM approach is tied to computation. It is more about discrete objects and computation than real-valued objects and things like analytic functions. Okay? So what is the tight computation class learned by LLMs? This is a huge question. You solve this, you'll solve length generalization, and we're all out of the job. So please solve this question. So it's going to be a new model of computation. It's not exactly what we have before. And empirically, once we understand this better, we can solve some of these problems, like length generalization. Let me just point to some works that I really like. So I should just say up front, I haven't read this paper, but a lot of people told me to read it. People are investigating programming languages, which are some kind of simplifications and views of what the transformers are doing. And they use this as a formalism. There's a lot of circuit complexity views. I'm just mentioning a few authors, Bingbin Liu, who just got married. Congratulations. Serbi Goel, Akshay Krishnamurti. They have this shortcuts paper about learning automata. There's a lot of papers about circuit complexity. I should say that here, the difference with how the deep learning worked is we make conditional bounds. So what Clayton Sanford and Daniel Su and nominally or minimally myself proved was that if you make some assumptions that I'll show you, you get then you can get strong separations under assumptions that are actually practically relevant. So I promised I will go fast through these slides. I will have to post these slides. I'll figure out a way, just check my website or email me or something, because I laboriously made an animation of one of these algorithmic problems, and I don't want it to go to waste, so just check the slides later. But basically, the story that I'm going to omit is that in a very clean way, transformers actually learn algorithmic tasks, both mathematically and empirically. So I'll just tell you this slide in one sentence. There's a beautiful task that the Anthropic identified called the induction heads task. Alberto Bietti, who I think was in the audience, also worked on this. So Anthropic, they identified this induction heads task, which is sort of like if somebody says dog, the next thing you think of is the last dog you saw. Okay? They found that this is a feature that's learned automatically to solve many other linguistic problems. They found that it naturally arises if you just stare at the attention matrices. So mathematically, Clayton and Daniel, and again, minimally myself, found that you can make a k-depth version of this. Like you iterate it k times. The magic is there's a log k construction, and then the insane magic is that gradient descent learns it. Okay? You can just download the code and run it. I run it on my home GPU. No like cloud nonsense. Okay? So again, the magic here is that there's some crazy computational task. There's a crazy minimal construction you come up with mathematically, and gradient descent learns the crazy minimal construction at the optimal depth even. And it's easy to train. There was a paper actually yesterday that points out that under the SQ model of learning, this was in a deep learning session maybe 2 days ago, you actually have to do it with the curriculum. Okay, so, oh my God, I prepared a 3-hour talk. Okay, let me just say, so I'm just telling you for approximation theory, relevant separations, I'm just gonna tell you 3 problems. The first one was for MLPs, we never solved it, but you're not gonna get $1 million solving that problem. More valuable is to solve the transformer one, we still don't have an accurate characterization of the class. 3, now that we have chain of thought, it is a new problem. Many of the methodologies for non-chain of thought break down when you analyze chain of thought approximation. And here I'm proposing an explicit question. Identify a discrete sampling problem, like picking the next move in a chess game. Pick some abstraction of what oracles you have, what oracle model you have. You have a next token sampler, you have a way to verify positions, you have a way to evaluate positions, okay? And take a pair of methods and separate them. Say that on this task, using these oracles, the oracle complexity of one is better than the other, okay? I'm proposing such an investigation because chain of thought really is a much different paradigm. This test time search is a much different paradigm, and the approximation theory questions are much different, and we're really out in the deep end here. You can prove anything you want, and it'll be interesting. Let me just show you some pictures why I think this problem is cool. So I ran Stockfish. But when people say like AGI, SEI, I don't care. I actually want chain of thought to compete with Stockfish. Okay, this is what Stockfish does if you run it for a couple seconds. It gets out to 16 million nodes, 16 billion positions, depth 60, okay? imagine attention competing with this. That's my challenge. So figure out some theorem that can actually, and figure out some algorithm that can actually compete with this. Okay? As everybody knows, every attention method will completely break down if you try to backtrack within 16 million things. So this is actually, for me, my favorite part of this part 2. So I did 3 approximation theoretic questions. 1, for MLPs, it's still open. 2, for LLMs, find the computation class that tightly characterizes what they do, and this is completely open. It is not some known circuit class. And 3, for chain of thought, I'm saying it's a completely different problem. One way to make this problem precise is to pin down the sampling problem we're trying to solve, which is open. It's not clear what you're actually doing with chain of thought. And with an oracle model, prove a separation between methods. Okay? So I will take questions, and then we will enter the fun part of the talk with the remaining 10 minutes. I realize I'm going fast and people are annoyed. Yes, Vidya, hey.
I wanted to go back to the MLPs part of the talk for a moment
Sure.
and ask a very open-ended question.
Yes.
In your view, like when we start to go to more quote-unquote realistic architectures, in addition to depth, there are lots of other bells and whistles. I think convolution maybe being the biggest one, and there's things like batch norm and max pooling. Feels very hopeless to analyze all of these. Which, in your view, is the most important?
Oh God. Okay, you know, I have to tell you that. Okay, so I have 2 comments here. So comment number 1 is there have actually been very few architecture innovations in history. I don't know if you all are aware of this, but it's like 1 per decade. It is actually not fast. Okay, the ReLU, the convolution, and the batch norm are all from the 60s. Okay, then they were rediscovered by Alex Krzyzewski. But then, since then, we've just had a few innovations. So there are not that many, there's like 5. Take any one of them and solve it. So like things like skip connection, unknown what it does. Normalization, pick the simplest one, RMS norm, unknown what it does. So anything, so I would place them equally. I'll also say that personally, I've sort of given up. And what I'm doing is I'm doing a holistic analysis where I'm trying to find more general properties that I can use to characterize what the landscape looks like and things like that. So that's another approach. But yeah, kind of a vague answer. Sorry, kind of a vague answer. Okay, so here's what we will do now. Now I will truly laundry list the speculative questions because I want to get to the cultural part. So again, apologies for my classical mismanagement of time. I actually woke up today, so at least I managed that much time. I'll just say these 3 problems. So I had 3 speculative questions. I'll just tell them very succinctly. Number 1, I freaked out while preparing this talk. I feel like all machine learning is curriculum. I feel like every idea we have is simply some way to drip feed information slowly to the learner. Everything we have. And I'm saying that if you can make a theory about this, if you can make a theory that says that machine learning equals a curriculum concept, then you could use this to solve arbitrary problems. If your test error is not going down, just introduce a curriculum in some way. And I really mean everything. I don't just mean curriculum in the standard sense of a distribution over inputs such that you make the problems of increasing complexity. No. I even mean loss functions, right? 0-1 loss to the logistic loss. Logistic loss smooths out the reward. Okay, discounted reward, it smooths out the reward. Reward shaping, like the data proportions in pre-training data, more Wikipedia, you know? Chain of thought drip feeds the answers to multi-step reasoning, you know, like Nati's paper, right? You're drip feeding with the chain of thought versus the end-to-end that says like leap to a solution. Diffusion models are iterated VAE. You have it drip feed the transport mapping to you, right? I feel like all we're doing in machine learning is just curriculum. So if there could be a beautiful theory about this to say all these things are the same, and for any problem that you can't make progress on, just turn it into curriculum like this. Okay, that's crazy question number 1. Oh yeah, and I just made some plots, whatever. Figure it out another day. Question number 2 is even more insane. This is speculative problem number 4. We have not succeeded in making subquadratic attention, and it is disturbing. There's like an infinite number of reasons why quadratic attention is extremely dumb, and we haven't been able to replace it. Okay, I don't know if everybody's following what I'm saying. Attention is quadratic, it has like a million things wrong with it. Somehow we cannot beat it despite an infinite number of papers per day claiming they can beat attention. And so I'm proposing a completely different approach. I'm approaching taking an analogy to the von Neumann architecture. So stick to a small quadratic attention, but augment it with a data fetch, aka RAG, and have a way to make code be data. So why am I telling you about this? Again, we're stuck beating transformers. We need a new idea. My suggestion is to look at what von Neumann did. Von Neumann knew about Turing, said this doesn't work. He came up with the von Neumann architecture. And no one's ever implemented a Turing machine. It's always been von Neumann architecture. And so I said, since transformers are kind of like differentiable Turing machine, let's make differential von Neumann. If you find this interesting, check the slide and email me, because I might work on this. I will skip this because it's too weird. Okay, now in the remaining time, I will tell you about the crazy stuff. Can you guys tell me non-toxically how much time I have? Non-toxically meaning don't give me more time because of some reason. 7 or 8, I will try to take 4 so that there can be questions. Okay, so I boiled down the hour-long rant from NeurIPS to 2 slides. So 1, in terms of what is the role of theory, my friend Sivarma and Balakrishnan, I'm probably not doing as well as he did. He gave this beautiful version of this that I've been trying to refute for 6 months. It is the best, okay? If you don't know Siva, go give him a hug. He's a beautiful man. Just, this is the best. So he claims there are 3 roles of theory. 1, analysis of algorithms, mental models, empirical rules of thumb. If you want to do that, that's fine. It's a great thing to do. 2, design of new algorithms, okay? 3, rigor and pretty mathematics. Okay, you just want to do rigor and pretty mathematics. And that's great too. You don't care about generalization. You don't care about test error. You're just doing concentration inequalities because you like log sum exp. That's great. Okay, go do that. These are all completely fine. Where things get difficult is people try to fight about what you should or should not be doing. But these are 3 completely reasonable reasons to do theory. This is the role of theory. And I want to say that it would be really nice. So when people talk about incentives in machine learning, there's no nebulous incentives. They come from one source. People with hiring power create incentives. It is cut and dry, okay? So this is the stuff that gets me fired. So it'd be really nice if like promotion and things like that had explicit criteria, you know? If you do rigor and pretty mathematics, you will get tenure. Wouldn't that be nice? If you had such a statement, you know, my tenure is at my final evaluation right now, and who knows, you know, somebody might walk in the room and be like, this is what I care about, reject this guy, done, right, I'm gone. So that's the reality, and it's kind of weird. So for junior people, you cannot, of course, affect this so much. You have to hedge, and you have to absorb new tools. People keep asking me, how do we deal with LMs? You have to use them all day. You have no choice. I was sitting with a friend in a coffee shop. She asked me, hey, do you know this paper? I said, no. I load it up. I start reading it. She loads it up. She pops it into O3. She's understood the theorem before I've read the first sentence of the abstract. I feel like a clown. Okay, this is the reality. Since then, I use O3 to help me read papers. Okay. Conferences should shield popular topics and slower timelines. I'm trying to figure out how to make this real with the ways I can affect it. For instance, yeah, this is something, if you're chair of a conference, we can talk about this. Lastly, we have to adopt GPUs ubiquitously in theory. We are not competing. Theory is behind practice, not because of we're behind GPUs. GPUs, has everybody understood this? It's not humans doing applied research, it's GPUs. GPUs thumbs up or thumbs down the papers, right? The GPU driver release determines which method wins. Everybody's aware of this. It's like NVIDIA internal microcode is determining which empirical paper wins and which one loses. It determines SOTA. We're not competing with humans, we're competing with GPUs. So theorists also, we need to adopt GPUs. And it'll get ugly one day. We'll have a $1,000 grant, and we can use it either for a theorem proof, right? Because O5 will prove theorems as well as we can. So it'll be, yeah. So this was question 1. Problem 1 was there are 3 roles of theory. And the issue is that people are not clear about, it'd be really nice for a conference which just says, if you're one of these 3, the paper can get accepted. And that way, when you submit your beautiful math paper to Colt, and it's like, well, this doesn't have empirical, right? This happens to people. Some people, they get a reviewer that says empirical is all that matters. The paper gets rejected after getting submitted to Colt. Right? That's not great. So it'd be nice if there was some sort of clarity about what it actually constitutes a valuable theory work all throughout the stack. If conferences could say this is what we're sticking to when we accept or reject papers. if jobs and hiring and things like this, internships, not dangling paper carrots for internships, but saying, your job in this internship for the summer is to do beautiful math. Don't need to produce paper. Great, Okay. Number two, I've spent a lot of time trying to figure out why academia did not produce O1. By O1, I mean a small scale O1. I don't mean the thing that you talk to on the web. For instance, we had LLM plus MCTS. It's just such a small epsilon to get LLM plus COT. Everybody talked about it, nobody did it. I mean, this was a consequence of DeepMind work from whatever, 7 years ago. So it really troubled me, and I thought a lot about it. And I spoke to people at OpenAI, why did they leave academia? And I actually started to feel that academia has become a bit risk-averse and complacent in a few ways. And I do not have a good solution for all of you, but the punchline from this slide is I really think we need a new publication model. Okay? I think this is actually what's holding us, one of the things holding us back. I don't have a good solution here. It's something we can maybe talk about later if you're interested in this, but it's just funny to imagine the following. Imagine if instead of paper, and this is the last thing I'm going to say, and then I'll conclude. So imagine if instead of writing papers, we just had a Git repo that was globally public, globally accessible. It was just all theorems, okay? What would this look like? Well, first of all, okay, but let's just imagine, okay? So there's this global public Git repo. And let's say you figure out some new concentration inequality. You can just go in, and instead of per 6 months, publishing a new paper where you apply your concentration quality, you can just grep and just replace it and just improve 1,000 papers or 1,000 theorems at once, okay? Because the reality is that all of you are brilliant people. All of you know so many things other people in the room do not know, but it takes you 5 months and stress about getting scooped to get this information out for one task. If we could just mix and match people and problems, a lot of things would move very quickly. So I should say that we do have some empirical information on this. It's the polymath projects by Terence Tao. So, they're heavily popularized and involved with Terence Tao's involvement. So I do not have a good message here, and the best message I could have is I could tell you I was doing this myself. But I will post these slides, but I do have serious concern as a discussion topic that we did not produce the O1 family of ideas. I find this very, very concerning. I think we're actually being a bit complacent that we didn't question ourselves about this enough. So I'll summarize these 2 questions, and I'll take attacks and questions. Feel free to attack me. That sounds optimal. And so for the role of theory, this slide by Siva. So analysis of algorithms, design of new algorithms, rigor and pragmatics, all greatly equal. We should just accept all of these to all conferences. And then the role of open science. This is many things, but the main thing about industry for me is the attack on open science. You go to OpenAI, you stop publishing. That's actually the real decision for me, and I'm confused. This is a hard decision to make. So that's what this is about. Okay, I will take questions, and I apologize for not managing time well. I see a few hands.
Yes, I'm just curious what exactly you mean with the O1 thing. So as far as I'm aware of, there have been attempts in academia, before O1 came out, to do RL on these things, and they actually improved on math quite a bit compared to the models without it. It's just presumably because of the lack of the scale, did not get that much attention. So I'm curious what exactly, more precisely, you mean with that claim.
Yes. Small scale. I do not understand why academia is not investigating small models. I have zero understanding of this, and it makes me pretty angry, actually. I spoke to OpenAI, and they asked me, why isn't academia doing follow-ups to tiny stories? Why are we doing small models? I mean small models. And to make it completely precise, when you go back to chess, I mentioned LM plus MCTS. This was a method being used. 1 million people in the world, including academics, were discussing, is there any way to remove the MCTS and do the algorithm inside the transformer? Everyone talked about it, nobody did it. This is totally small model. It's totally feasible to do on my GPU at home. And it is confusing for me that it did not happen. all of these things, they don't make $1 billion, but they are interesting on a small scale, and it confuses me it didn't happen. So yes, my answer is small scale, and I'm, as a corollary, very concerned and confused why academia is so obsessed with the large models.
Thank you.
Uh-oh. I'm eating lunch.
Could you expand on what you mean by a small model, though? Like, I mean, academia, like, we already are using, like, 1.5 billion parameter models or 1 billion parameter models, right? Like, we are fine-tuning, like, Gemma and Quen and everything like that, right? Like, if you go too much smaller than that, then empirically it seems as if you can't really do the kinds of reasoning.
Yes.
And, like, and if you get to that scale, I mean, you're not going to be running that probably on your MacBook Air or whatever. So.
Yeah, so here's another open problem. Take what you're calling reasoning and just deconstruct it into an orthogonal set of actual mechanisms. And I would be really shocked if you can't exhibit those on like a 1,000 parameter model. That is my claim.
But isn't there still some kind of like coordination issue where, like, even if you and I agree that some graph task that you could train on your laptop is reasonable and interesting, and I certainly agree that it is, I mean, like, it's not clear that that's going to generalize to some other graph task or kind of actually be kind of interesting more broadly. And I think, I mean, aren't people, like, one of the reasons that we have these like larger benchmarks for math is that somehow everyone agrees that like improving math is like kind of important. Right?
So I'm in total agreement with you, but there is no public refutation that none of these phenomena cannot be replicated on a small scale. And that is actually very strange. So you're appealing to like common belief that these things have to be done at large scale, but there is no mathematical refutation of that.
What would refutation look like?
What I'm saying is that actually characterize the underlying, divide what you're calling reasoning into a bunch of nuts and bolts phenomena, and then determine the small scale where they can be exhibited. I mean, I'm taking an approximation theoretic viewpoint on this. Like, let's look at the actual sampling problem that lets you get to the solution to a math problem. And let's break this down really precisely. Okay? Like, what's being done at every step of the chain of thought? How much computation is needed? What is the actual mathematical sampling problem being solved? I mean, it's really hard for me to imagine that there isn't like a 10-dimensional version of that problem which already has many of the phenomena exhibited. But again, I'm making an appeal to belief also, but there is no refutation that these things can't be done on a small scale. And when I talked to Ronan Eldon last week about tiny stories, he said he believes that many of the phenomena found in large models can be replicated in small models. I don't have information, right? I'm just saying it's a belief.
But even like models trained on tiny stories are using like a few 100 million parameters, right? Like.
Yes, because human language is based on this thing, which has also a few parameters. So, but if we compete on a task where our benchmark has fewer parameters, then it's a philosophical point. What is reasoning actually? I hope it's not just complexity, is my point.